Thanks for showing up. What I've done here is kind of tried to tie in some things of interest here on the campus. I know when I came in for my interview, people were very excited to talk about compostable plastics and why they don't break down. So that's at the end of the talk. There'll be a few slides on that. I think the people that are really working on it know why they don't break down. But for the general audience, we can cover that. Okay, so understanding plastics, a little bit what they are. Okay, the idea, I'll give you an introduction to polymers. Okay, I'm going to use these terms interchangeably. All right, if you're really a kind of plastic nerd, you'll yell at me and say that's not true. You know, there's this thing called plastic deformation that things have to undergo. We're not going to worry ourselves about that. Okay, for the most part, we don't deal with that. Okay, so if I use the word polymer, I use the word plastic. Cool? Okay. All right, so go through the common polymers and their structures. There's a lot of misunderstanding. I think everyone thinks that the different polymers, at least the recycling numbers, while they have different names, they may be the same thing, and that's not true. Okay, so we'll go through what each one is. I'll talk a little bit about plasticizers and polymer processing, how your cup is actually formed. Okay, that's a pretty interesting part. There's actually PhD projects in this subject matter alone. Okay, so it's pretty intricate in some ways, so we'll just kind of scratch the surface on all of these topics. Okay, if you want further information, come see me. Okay, then we'll get into the kind of the concern. Ooh, 5 disappeared. We'll get into the topics that I think are most interested here on campus. This idea of biodegradable or renewable plastics. We'll talk a little bit about compostables, and then I'll give you my conclusions. Okay. All right. For the most part, yeah, as I said, plastics are going to equal to polymers, and the idea that we start out with a monomer. Okay, that's just a small molecule. We can think of that as most chemicals that we know in the world. Okay. This one is styrene. If you polymerize this, okay, I'll tell you what that really means, polymerizing it. You get polystyrene or styrofoam in some case, okay? That styrofoam is actually expanded polystyrene. That's just air has been blown into the polymer, okay, to blow it up. So what you do and how you would make a polymer, okay, is you start out with a bunch of these monomers, millions of them in some cases, all right? And you add 1 and 1 and you get 2, and they just stick together, okay? The head groups stick together, and this would be your typical chemical reaction. If you're an organic chemist, pat yourself on the back, your job's done, okay? You've done this one thing. If you're a polymer chemist, you're really bored. You say, that's so small. I like things to be a lot bigger than that, so you keep going. You add another one, and you get 3, and you keep going and keep going and keep going and keep going, okay? And you wind up with this, okay? And sometimes you'll get up to 5,000 of these added together, okay? So you can kind of think of this as a super molecule, okay? What you really get when you look at your plastic cup, all right, it's not one molecule. You have a bunch of them in here, okay, combined. And there'll be a bunch of differences. So there may be chains in here that are 4,000 repeat units. There may be chains that are 4,500 repeat units, okay? It's a mixture. You can never do like a set every single chain has 5,000. That's really, really precise, okay? Polymer chemistry is pretty sloppy in that sense, okay? But really, you kind of get the idea that it's good enough, and when you get the properties you want, you stop, okay? And this is really what kind of people think about when they think about plastics, right? The big blob. So you kind of think of this plastic blob coming to get you, you know? In some ways, it's kind of, that's what most plastics look like, okay? Or you can make them look like that. But the thing is to reform them and to make them into useful shapes, okay? And useful products, okay? So common plastics, these are what most people in the room know. And really we know plastics based on, because we have this recycling chart, okay? And so each one of these numbers corresponds to a different type of plastic, okay, or polymer, and each one has a different chemical structure. Okay, these are the common ones, PET, polyethylene terephthalate. This is mostly your Coke bottles, plastic Coke bottles, okay. Polyethylene, high density and low density, okay? That's your shopping bag, your Ziploc bags, okay? Polyvinyl chloride, this is our PVC pipes that we see. And if you look, each one of these structures, okay, the structure of just the monomer, the starting material, will dictate the final properties, okay? So if you see this benzene ring, benzene is a pretty rigid molecule, especially when you hook it up and attach some side chains on it. Okay, it doesn't really like to bend and shape. Double bonds are pretty strong in that sense. Okay, so this is going to be a tougher material than, say, this linear chain of just carbon. Okay, if you just see a linear chain with carbon, 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 it's basically wax. Okay, candle wax. You can kind of think of that. All right, animal fats, and a lot of these contain long chains like this. Okay. So that's why your plastic bags kind of have a waxy feel in some cases. All right, these melt down really low, really low temperatures. Okay, if you just replace or you add a chlorine atom onto this, chlorine is a really heavy atom. All right, so you can get things like PVC, which is inherently a flame retardant material. Okay, so that's why you see a lot of PVC used in wire and cable industries. Okay, because it's inherently flame retardant. Right. It's also one of the problems when it burns. It releases hydrogen chloride gas, and why it's a problem. Okay. So some of the other ones, polypropylene. Okay, looks exactly like polyethylene, except it just has the branch, kind of same structure as PVC, just a different chain, different molecule here, completely different properties. Okay, because of that result. All right, these tend to be a little bit tougher. These are the reusable shopping bags that you get for $1 at the store nowadays. Those are all polypropylene. All right, a lot of our plastics are made, plastic cups and things are made out of polypropylene. My cup is actually made out of polypropylene, but my lid is made out of polyethylene. Okay, and they serve different functions and they have different properties. Okay, that's why they correspond to what they do in some mess. This has to actually hold the liquid. This has to just actually prevent it from spilling. Okay. So everything is kind of tailored to what it's used for. If someone asks me how to make a polymer, I'm basically going to come back and say, well, what do you want to use it for? Okay. All right, and we'll get into that a little more. Here's polystyrene. Everyone knows the idea of styrofoam. Okay. And then here's the ones about the other polylactic acid. This is the cups we have on campus. All right, a lot of the linings are now coming. If you have the paper cups, coffee cups, most of those are now PLA lined. And then polycarbonate. Does everyone know polycarbonate? The big problem with polycarbonate? I thought I heard it. BPA, yeah. Bisphenol A, okay? Everyone thinks that polycarbonate is actually the problem, okay? It's not. It's the monomer, okay? So it's unreacted material that is actually in the plastic, okay? If you look at just this benzene ring and that OH, these two benzene ring and that OH, okay, that's actually bisphenol A. I'll show you the structure in a minute, okay? As a whole, this polymer is not going to harm you. Okay, but as it breaks down over time, or if you have any unreacted monomer that's trapped in there, that will eventually leach out and come in contact with you. Okay, so that's where you get the problems. Okay, so with all of these polymers, the polymers themselves, for the most part, are non-toxic. It's all the stuff we add into them to form shapes like these, typically, that are the problem. Okay. All the small molecules are the problem. All the big molecules tend to be fairly safe. Okay. If you were to ingest, I'm not suggesting you do this, some polylactic acid or some polycarbonate, it's going to pass right through you like cellulose would. Okay. Because your body is not really adapted to deal with such a large molecule. Okay. All right. To kind of show you about, back to my comment about if you want to make a polymer, I'm going to tell you about what you want to do with it. The idea of copolymers has really come in recently. Okay, we've been making them forever. Your proteins are copolymers in some ways, okay? But the idea of new plastics and all the ones that are coming on the market, those are copolymers. And so they're tailored to specific applications, okay? And so the idea here, and these are just examples, you could insert whatever property you wanted up here, okay? I chose flexible because I can draw a little flexi chain in the middle, okay? So this guy has a waxy tail in the middle. Here's rigid. This is bisphenol A. These two, again, benzene rings are really rigid, okay? So that's why bisphenol A is added into it. That's why polycarbonate you can drop off the Empire State Building. It won't break, okay? This is actually the compound that bisphenol A has been replaced with in your Nalgene bottles now. It doesn't have these benzene rings here, all right? It doesn't have these OH. It has these OHs to still attach. So this OH can be viewed as this little green dot, okay? And that's where it attaches to the next molecule, okay? So this does not look like a hormone, essentially, but this does, okay? So that's the problem. So if you replace it with this, you can get similar properties, okay, without the problems associated with it, okay? All right, so back to the idea of tailorable polymers. What you can do is, in the same way that you made the first polymer, if you had all of these, that would be called a homopolymer. But if you start to mix them, you can get what's called a block polymer. We have a bunch of flexible chains here, say, and then you have a rigid section, okay? This would be called a block copolymer. You have alternating copolymers where each one alternates, and then you have random, okay? And the properties of these are going to vary differently, okay? Really, you have to find an application that you're looking for, okay? And then it's completely tailorable from there, from that point of view. All right, some common copolymers that we see, okay, that you associate. Nylon is a copolymer. All right, here is one of those monomers. It tends to be semi-flexible on both of them. So this would be the idea of combining two different flexible molecules together, okay? Here's one monomer. This is a diacid. And you combine it with the diamine, and you would get this nylon string that you're associated with. The exterior of most of your hiking backpacks are made out of nylon. Pretty tough material, okay? That toughness is a byproduct of this bond here, the Mi bond. It tends to be a fairly rigid bond, okay? Your proteins are kind of the ultimate copolymer, okay, with many, many monomers that come together, okay, to combine. You start to attach all of these. Each one has an amine, each one has an acid group, and then you can kind of get to your protein structure, okay? So does everyone kind of get that idea of tailorable materials? Yes?
An alternating polymer, how would you ever convince that to actually line to alternate it? It seems like it'd be very easy to make random ones and very hard to get alternating ones.
Yes, you have to use special catalysts, expensive catalysts to do it, essentially. So, and a lot of times what you do is you put one molecule on, and then you stop the reaction, you put another molecule on, stop the reaction, put another molecule on, stop the reaction. So it can become very tedious in that sense. But that's really what you're going towards in next generation materials. There's a lot of that out there. Perfect example of that is what's going into, these are conjugated polymers, okay? These are unlike any plastics you've probably ever seen before. All right, the difference here is that every other bond in this polymer is a double bond, okay? And what that does is it means electrons can hop along the chain backbone here. And so these have a lot of electrical application, optical applications. This is the backbone of organic light-emitting diodes that are coming out now. This is the backbone of flexible solar that's coming out. Okay, this is a company called Kanarka. They started at UMass Lowell. One of the guys that was on my faculty committee was part of this. Really cool company that's out there. They kind of set the world record every other year. People trade for best plastic solar cell, okay, that are out there. If you're in my class, if you're in the Chemistry 1 class or the Organic class, I'm having one of these shipped up to us now. It doesn't work, but you'll be able to see it, okay? They won't send me a working model, but you will be able to kind of see the difference. This is a new kind of solar shade they're developing. They make these in all different kinds of colors that are out there. Okay, and these are all plastic based. Okay, not only are these have these conjugated polymers on them, but this is actually a PET backbone. All right, so it's basically a polymer on top of a polymer, laminated. Okay, so it's kind of the all organic material here. And there's even some lightweight batteries. Okay, that can be developed. So a whole nother type of field. Okay, these are conductors versus typical plastics that we always think of as being insulators, right? Okay, so all kinds of crazy polymers and plastics out there. Okay, so how do we actually go about making things like our cups? This is kind of a rudimentary overview of some of the technology. I won't go in through all of them. Okay, most of it is called, most of the kind of form shapes that you see here, tubes, plastic pieces. Say the cap that would go on top of my laser pointer. Okay, you want something like that. This cup, potentially cap. All right, all of these things can be made by extrusion. And what happens is you have these pellets. Okay, this is your actual polymer. You've done your polymerization. Okay, and you've added your dye because you want it to be purple. Okay, I really want a purple laser pointer, so I'm going to use that one. And I'm going to basically throw it in this hopper. All right, and everything goes in. This is where it comes in. And there's a giant screw that runs along this. Okay, sometimes there's two of them together, and basically they start to grind up that polymer into smaller pieces. And all the time you're heating it, so you're starting to melt the polymer at the same time. Okay, but a lot of, if you didn't add an additive, it would basically burn out the motor on this. Okay, because the polymer doesn't really, it's kind of a, you can think of it as like a super viscous material. Okay, like molasses on steroids. Okay, so that is the reason why we add all those kind of nasty plasticizers. Okay, because they wind up getting in between the chains of the polymer. I'll do my best to draw. I'm not the best artist, but whenever you draw a polymer, it doesn't really matter if you're an artist because it looks like a big piece of spaghetti, okay? All right? Polymers basically are called random walks because they just kind of go anywhere. Dave, you'll probably notice this is fractal, some kind of fractal. So this would be, you can kind of think of this as a collapsed polymer, okay? And what a plasticizer does, okay, is it takes this kind of tightly coiled thing and spreads it out, okay? And so you can kind of think when you have something like this, I know you can't see that, can you? No. Blue is a bad choice. Think of it being like a tight ball, okay? And then when you add this plasticizer, it starts to spread out and swell, okay? So there's a lot more movement available if you're spread out. Does that make sense?
So that coiled up thing, is that one pellet, or is there many of those in each pellet?
There's going to be a lot of them. Yeah, yeah. That's a hard concept to kind of grasp, that you have this super molecule, okay? But there's really a lot of super molecules together there, okay? And depending on the distribution of the super molecules, how big they are, will affect its properties too, okay? But for the most part, you got to think of rigid material, you're adding it in, and then you have to add these plasticizers to kind of spread it out. And once it's all spread out, it becomes much more like water flowing. Okay, not quite like water, but corn syrup flowing as opposed to molasses. Okay, and so as it moves on down here, you can add various other things to it. If you're making rubber in some cases, you can add carbon black and things along the way. Okay, if you wanted to strengthen your material. There's a vent in case any gas builds up. Okay, you don't want any bubbles to form. Okay, those would be called blims, and then essentially it would show up on the surface. Okay, as a hole in your plastic. And so then after it comes out the end, that's this part. There's a die here, which would basically look like a tube. Okay, and it would just squirt out a tube out the end. Okay, so that's how extruded parts are kind of made. It's pretty simple, okay, but people spend their lives designing these screws in various shapes, and they get different shears and everything to actually mix things very well. It's just a giant mixer. Okay. Same exact idea for these blow molded parts. Okay. Here is the screw coming through. Okay, and instead of shooting it through a die, we shoot it into, say, open mold here. Okay, if we want our mold, our bottle in this case, to be hollow, we just blow air into it. Okay, so we shoot some plastic into it, we blow air, all the plastic will form to the sides. Okay, and then we cool the outside of this, because remember, it's hot coming through here. We cool the outside, the plastic will condense on the sides there, or solidify in some case, and then you get a plastic bottle that pops out. Okay, that's called blow molding. That's how our bottles are made. Okay, injection molding is the same idea. Okay, except really you're not injecting air into it. Okay, you have a set mold. This is actually the mask that Michael Jackson wore during Thriller. They're using this as a model, and it was injection molded. Okay, so you got to think there's a plate that goes right on top of that. That is a mirror image to that. Okay, but probably, 2 or 3 millimeters of a space. Okay, and so you would basically just force the plastic in some little hole in the top. And it would kind of go around the edges and form that. Okay, that's how rubber duckies are made. Okay. Yeah, but all of this gets us to the point of some of the problems with plastics. Okay, especially when we're talking about this idea, because this is where people kind of have the visceral response to plastics for the most part. Everyone thinks they're kind of toxic. The problem with these things is that they're small molecules trapped inside of a large molecule. And over time, those small molecules can move around, all right? And as they keep moving around, eventually they kind of make their way to the door. One of them does, in that sense, okay? And then it goes out the door, and it's all of a sudden in your food, okay? And that's really scary for a lot of people. And there's really not a good way to deal with this problem. It's kind of a product of what we have to deal with a little bit. We can design safer things to put into it, is really the answer. That's probably the best I can tell you in that. Yes?
Ryan, could you just talk about the plasticizers? I mean, you talk about them sort of lubricating, creating space. I mean, what kind of chemicals are they? And obviously that's got heat and then there's less heat, so are some of them volatilizing, or where do they, those that aren't trapped, are they just waste products, or are they forever in there?
Well, it's a little bit hard, I can tell you. Some of them are like, this is the best example. The most common plasticizers, okay, you don't usually use a plasticizer too much with polyethylene, okay, because you don't really need to, because it melts and flows really easily, all right? But something that's more rigid, like PET, needs a plasticizer, okay, because it's really hard. You have this hardened material in here, okay? So an excellent plasticizer for polyethylene terephthalate would be to add a phthalate to it, okay? And phthalates are also the major component of plasticizer for PVC. And this is really the scary part, because these are the ones that people are really frightened of, okay? Phthalates look a little bit like bisphenol A if you look at their structure, all right? And there are some studies starting to come out that these are linked to hormone disruption, okay? So the idea of adding something that looks like this into your plastic is a little bit scary. I think it hasn't come out at all, and I'm not suggesting that PET is a problem in any sense. But when they make their way to the surface, they are a problem, okay? And it just takes a long time. Things that can speed it up are heat and soap, okay? Soap helps blur the surface between hydrophilic things like water, okay, and hydrophobic things like your plastic, okay? So if you use a lot of soap on, say, plastics, it will speed up and remove some of the plasticizer that is at least on the surface, okay? I'm trying to think about.
So that's like you don't. That's why you don't want to use a water bottle that's not Nalgene over and over and over because maybe the inside would be leaching?
No, an Nalgene is susceptible to the same things. Okay? They're all susceptible to the same idea. All right? Whatever is inside, if it's a small molecule, ultimately over a repeated use will make its way to the surface. Now the rate that it makes its way to the surface is different. Okay? And that's important. Okay?
Nalgene's just taking it along.
If it, well, I don't know. I don't know. It depends on what you add into it. Okay? I don't know the answer. Okay? That's the main thing that I can tell you is that I don't know what level of exposure to these chemicals you are allowed to be, allowed to have. Okay? And I don't actually know the rate of leaching. The one thing I can tell you is that heat will help move it. Okay? Just like if it was hot in here, we'd all be moving around a lot more, okay? Because we're hot and kind of miserable. Same idea with small molecules trapped in a big one, okay? It starts moving around, it really wants to get out that door, okay? And so that's the idea. That's one of the reasons why you don't really put plastics in the microwave or in your dishwasher. These all speed up leaching.
Can you say a little more about the heat, because the pellets are formed with the plasticizer in the extrusion process via heat. How much heat is that, and how much heat, sort of at what level does heat really speed up the process, or is that not?
At all levels, it speeds up the process. That's just the
But
kinetics, natural
okay,
phenomenon.
but more at a certain, is
That's
there a
right.
threshold?
So the idea is, if I'm going to process a plastic, for the most part, you're going to process most plastics somewhere between 50 and 100 degrees C.
Mm-hmm.
All right? We don't usually hang out in 50 to 100 degrees C. Okay? So the rate that these things happen, right, we have to heat these up to, say, 80 degrees C to even get it in the middle. Okay? And once it's in the middle, it's got to make its way all the way out to the surface. But it's only making its way out at the rate that 20 degrees or 30 degrees C will afford. Okay? Which is on the order of a couple orders of magnitude slower than it goes in. Okay? Does that make some sense? Yeah. So there's a lot of questions. Yes.
So, like a classic example of like a water bottle sitting in the sun all day. It's
Yeah.
being beamed with heat radiation, and then someone goes to drink it, and they're like, "Oh, this water tastes like plastic." Is that literally plasticizers and monsters? Is that possible that happens, or what is contributing to that? Is that something in the industrial process, or? Because we've all had water and food that tastes bizarre.
Yeah, yeah. It all depends on the age and how many times you've done it. Is really the answer.
And
So
so I guess my question too is, can you taste plasticizers? Like, is that actually what's going on, or?
I have no idea. I've never tried. So I would assume you would taste something if it was there, but I don't know. I don't know.
There are
So
lots of other additives that it could be too.
that's right. There are a lot of other additives that are and things. So a lot of times you'll add something in to keep the plasticizer hanging out longer, okay? So to make it more happy in the inside. So yes.
Is this why you use a metal water bottle?
Well, it depends on this. See, this is a whole other thing. Depends on what metal water bottle you're using. If you're using an aluminum water bottle, it's got a epoxy liner on the inside of it. And some of the epoxies are just as toxic as bisphenol A. So, sorry to scare everyone. See, all these hands go up, yeah. So really, this is where it becomes an idea of consumer choice, okay, and knowledge, all right? If you don't know what type of material you're using, find out, okay? And write to the company and ask them, what are you using plasticizers, okay? In here, what plasticizers are you using? What is the time it would take to leach out? Okay? They know that data. They may not tell you it. But the more people that ask, the more of a response you'll get. Hence why Nalgene made a dramatic change. They've changed their process completely, okay, because of consumers. Okay?
So what you're saying that Nalgenes are not using plasticizers? Because I'm wondering.
No.
All right, good. Because what kind of plasticizer doesn't help me? Because there's no plasticizer that's actually not harmful for me. Or is there some?
They use lignin as plasticizer.
Okay, that's good.
Okay, wood, pieces of wood, essentially.
Okay.
You just need anything to get in between the polymer chains. Okay, the reason why small molecules and so plasticizer is a grab-all term. Okay, they use particular compounds are the things that are going to be toxic. Not all plasticizers are toxic. Okay, you can take a smaller polymer that only has 100 repeat units and use that to plasticize the same polymer that has 5,000 repeat units. Okay? So it's just anything that can kind of squirm in and spread the chains apart. Okay? That's the plasticizer.
So is it a physical process and not chemical?
Yes. It's a,
Just little things?
well, there's interactions between bonds that are going to hold it up.
Right, okay.
So
Yep.
things like hydrogen bonding can come into play. Okay? Those are that's some of the ways they use it. So they'll use like chemical interactions to keep things inside longer. Okay? They'll use heat to get it in there and then rely on it. I got to keep going. I'll get all of these questions. Okay? We'll never kind of get through it all, I think. So I knew that plasticizer was going to cause problems, because that's why everyone's here, right? Everyone's scared of plastics. For the most part, the plastics are okay. Yell at people about their plasticizers. Okay? Or their poor polymerization, which is the problem with bisphenol A. Okay? All right, so problems with plastic. We talked a lot about this. Okay, everyone has probably heard about the North Pacific Gyre. It's a big trash bin, basically, where plastic winds up accumulating off the coast of California. All right, see it here. The currents kind of swirl, and in some cases, trash just tends to accumulate there. Okay? Plastics, particularly in seawater, won't degrade. Okay? You think they degrade slow on land, throw them in cold, salty water, and watch how long it takes. Okay? We won't be here, essentially, to see it. Okay? But the problem is that plastics, when you throw them in water, okay, most plastics are hydrophobic. Okay? That means they're going to absorb all the oils that's on the slicks, basically any kind of plasticizer, things like that, that is in water will kind of tend to lump into this. Okay? It's like a sponge for anything that is hydrophobic, and it just soaks it all up. Okay? And so it concentrates it, and will basically concentrate a lot of toxic molecules essentially in one area. Okay? And kind of kill everything that's around there. So it's a pretty big deal. And of course, everyone kind of knows the effect, or at least seen pictures of the effects that it has on animals. So this is a turtle, essentially with one of the milk rings. Okay? He happened to kind of walk through it when he was a little kid, little turtle, and now he's grown up with this thing, been deformed by it. So it's a real problem. Okay. Here's an overview. Kind of this is the trash piles that have been here. Okay. There's all kinds of crazy stories out there. Nike has lost a bunch of containers, shipping containers, where they dumped 20, 30,000 pairs of shoes into the ocean. Haven't recovered any of them for the most part. My most favorite story about it is this one, when in 1992, 28,000 rubber ducks dumped into the ocean. And they wound up watching these, and so most of them wind up circling here, okay, but then they've actually followed the currents where they take them, and you've had them make their way all the way over to Europe. Okay. So this is a book that was written about it. I love this. True story of 28,000 bath toys lost at sea in the beachcombers, oceanographers, environmentalists, and fools, including the author who went searching for them. If you want this book, if you really want to read this, I have a copy of it. It's on my shelf, so come see me. I haven't read it yet, so you have to bring it back. Okay. But this kind of goes, okay, to show that these things aren't breaking down in our environment. Okay. This is 15 years later, and you're still finding them. Okay.
How do they know they're from that shipment?
They all have markings on them, so they know. All right. In terms of plastic production, the one thing you should know about plastic production is it's not slowing down. It's rapidly expanding. Okay, because of the tailorability of properties, plastics are here to stay. Okay, The only thing we can do about it is really smartly design them, okay? One is to be recycled. Two is to better design them for their use in that sense. So you see up here the largest percentage of plastics are going into packaging, okay? Most of our packaging is single use, okay? And then we throw it away, right? So a really smart way to think about this is that if we design our packaging essentially to be compostable, okay? As opposed to a single-use item that's going to hang around for 100 years versus a single-use item that's going to hang around for 180 days after its use, okay? Now, you have to take into account that that item also has to sit on the shelf, okay, in its package. So there are other concerns. Not everything can be made out of a compostable plastic, okay? So there are modifiers that have to be added into that, okay? But if you can tailor it to, say, break down after 2 years on average, you're getting there, right? Yes?
I'm just wondering why the real question isn't, why does it need to be disposable in the first place? Why can't we have something that's reusable?
Well, we try that, right? We actually try. It's called recycling, right? And it's only a partial solution because we don't get it all back, okay? I know this is a terrible graph. You can't, and that whole side of the page is cut off. This is in millions of tons, essentially, okay? So you can see it's a lot of millions of tons over here. And this is plastic generation, okay? This is, the data is 2003 is when it cuts off. And this is the U.S. recovery, okay? They're diverging it.
Generation in the United States.
Yeah, okay? U.S. recovers less than 6% of its plastics, okay? Europe is much better about that, greater than 20, and then some of the other countries in Europe are even better, okay? I imagine that reach that's gone into Europe since this effect has even helped this problem, okay? Because manufacturers are becoming more conscious of what they're putting into it, all right, and demanding back things, okay? REACH is a regulation that went in that basically says that if you make something, you're kind of responsible for its toxicity in some ways, okay? You can kind of think of it. It basically just puts more ownership on the company, okay? It's kind of a broad generalization, okay? But it's a decent way to think about it, okay? So clearly, recycling is not an answer, because it doesn't really work, okay, for most part. It's really good. Recycling is really good for polyethylene and polypropylene. But we don't have disposal infrastructure set up to deal with a lot of the other ones. That's why if you go to certain places, they'll only take certain ones, okay? And a lot of times, it's a lot cheaper to buy virgin plastic than it is to buy recycled plastic, which is really dumbfounding to me. But a lot of times it takes a lot more energy to melt down, remove the stuff that was in the old plastic to make it a new plastic. And when you melt it down, what you wind up doing is take that giant polymer ball and start chopping all those chains up. So now all of a sudden, it's not a giant chain anymore. It's a lot of half giant chains, okay? And by cutting those in half, you change its properties significantly, okay? So recycling, in that sense, should never be called recycling. It should be called downcycling, okay? Because you have a lower value material at the end, okay? Very rarely do you get a truly recyclable material. Okay, so the idea is moving to designing renewable polymers, okay? And really, the design principles look a lot like the ones that we have now, which is important. We can't change the game too much, okay? We have to kind of fit into the infrastructure that's already in place, all right, to really make it happen. So I'll go into what bio-based is, okay, but you can see this process is pretty similar to what they use now. You take a feedstock, whether that is agricultural or petrochemical, okay, and use that to manufacture a product. You have to put in energy to do that manufacturing, to make that product, say to form this plastic cup, okay? That costs you energy. But then you design for ultimate disposability, okay? There's a lot of people that write good essays about how to do this, okay? This idea of transforming the product after its first life into a useful second life, okay? William McDonough wrote a book, a whole book on it. If you take sustainable material development, that's one of the assigned books. So we're going to read that. You're going to think about it, okay? This idea of a second life for your coffee cup when it's done. What could it be, okay? And then this is really the idea of smart design, okay? Single-use, short-lived, disposable materials, okay, should be bio-based, okay, compostable in some case, and should be engineered to retain its biodegradability, okay? If you take something made out of a feedstock and transform it into something that is non-biodegradable, you're really not doing a lot of good, okay? Perfect example of this is that Coke and Pepsi have now come out with plant-based. Have you guys seen these ads? The plant bottle, okay? I don't know how they do it because I haven't looked into the chemistry of it, but a lot of them are saying that they're making polyethylene terephthalate, okay, out of corn, essentially, is their starting material. So corn in, you can kind of think of the black box, corn in, polyethylene terephthalate comes out. Your plastic bottle comes out, okay? Polyethylene terephthalate is not compostable. It's only recyclable. So you're not returning those nutrients to the fields, essentially, to our grounds, okay? You're abstracting those.
Plus you're using a lot of corn that you could be.
Yeah, that's a whole nother argument, okay? People use corn because it's a lot easier. You're essentially dealing with the problem with starch and cellulose, okay? Starch breaks down really easy to give you sugar, which you can then ferment to do things like make ethanol or lactic acid, okay? Cellulose is just a beast, okay? It's really hard to break down, okay? And so that's really why you don't see a lot of people using wood to do these things, okay? There's a lot of cellulose out there, okay? So if someone can come up with a really good way to do that, you have a process, and you have everything is in place already for you, okay? You can basically turn a lot of feedstocks around. A lot of products can be bio-based from there on out, okay? If you can break down cellulose as opposed to starch. All right, this is what we're all talking about, okay? This idea of sunlight gives us photosynthesis, right? We use our natural resources. We make a polymer out of it. This is the plastic we were talking about. We process that. We use and discard. It biodegrades, okay? Nice, clean cycle in some aspects, okay? So that's really what we're striving to get towards, okay? Now, when you look at, this goes into being a smart consumer. I'm going to pass these around, okay? And I'll be talking them as I go. Things to note. I don't know if these bags say it on there. They do. Yeah. Okay, different types of bags. I'll just pass everything around. You guys can play with them. Okay. Here is the newest product label that you'll see out there. These are plastic bags. Okay, these are polyethylene Ziploc bags. Okay. And these say bisphenol A free on them. Now, you're sitting and that should make everyone laugh, okay? Because there's no way you'd ever put bisphenol A in polyethylene to start with, okay? It was never in there. That's like saying you're going to put bisphenol A in broccoli. Okay? So, you see a lot of this now, okay? And that's one of the things. So you can take a look at it. It says somewhere on here, bisphenol A free. BPA free, right? No one knows what BPA means, but that's the idea. Everyone knows it's scary. All right, this is a bag I found in downtown Bar Harbor. I don't know if we have these on campus. These are the dog bags. Okay, we'll talk a little bit about what these are. This says oxo-biodegradable on it, okay? That's also a polyethylene bag. And these are the certified compostable bags, okay? And these are certified to be compostable, okay? I'll tell you what that means too, okay? If you look on here, you'll see it says it's certified by, what is the company's name? BPI is the initials, okay? Bioplastics Institute. And this says it conforms to ASTM 6400, okay? So that means there's some test for compostability and it passed that test, okay? So I'll tell you what that all means. These are actually starch-based, okay? These are a blend of starch and a non-biodegradable material called polycaprolactone, okay? They just blend in so much starch into here that these wind up breaking down to the acceptable levels, okay? All right, so you guys can play. Feel the difference, a pretty big deal between the two of them, okay? All right, so what do all these terms mean, okay? This is what I just talked about. The FTC talks and will prosecute people, or at least fine people, I think. Tell them to remove labels if you find that you are kind of greenwashing your product. If you call something biodegradable and it doesn't meet a certain standard, to use that term, okay? And then this idea, getting to this idea of actually using renewable resources, this term bio-based has been born, okay? Bio-based essentially means that you're using newly fixed carbon, newly made carbon, okay, as opposed to fossil fuel carbon, okay? And you can actually test for that. So if you really wanted to make sure that this bag was bio-based, okay, you could do carbon-14 dating on that, okay? And people do, okay? So what you wind up seeing is that there's only a small amount of carbon-14 out there, all right, but there is enough that we can find it, right? And the half-life is 5,730 years, okay? So if something's 1 million years old, okay, there's not any carbon-14 left is the purpose. So you can tell if you have carbon-14 in your plastic or in your material, it's new carbon, okay? It's recently, okay? So there's a big test for this. This is kind of the idea, and there's a calculation that's a little bit confusing. Here it is. I'll tell you, I mean, so, and it's going to make you scratch your head, okay? So if you have, there's a reason why I'm telling you this, because there's a new certification process that if you buy something, it'll say bio-based. Here it is, okay? The USDA now has these new labels that are coming out. Look for these, okay? I think they're pretty cool. I'm glad that they're out there, okay? They just released the new product. 7th generation has a lot of these, okay? Pay attention. If you see this level, they'll say product 50% bio-based, okay? And what that really means is that they threw it in this calculator and out comes 57%, okay? That doesn't mean that everything, 50% of the total material is bio-based, is new material, okay? It's just talking about the carbon that's in there, okay? All the little carbon atoms. So if you took glass fiber, okay, which has no carbon in it whatsoever, and then added it to polylactic acid, which is a new base material, that is actually 100% bio-based, okay, even though 70% of it is carbon, okay? Or less than 70% of it is carbon. But all the carbon, all the C's that are in here are new C's, see, new carbon, okay? Is that kind of the, understand that, okay? So here is the confusing example where you have cellulose, which you can consider new carbon, and polypropylene, which would be old carbon, fossil fuel based, okay? And then when you do the calculation to figure this out, it's not actually 30%, it winds up being 18%, okay? And it's based on these percentages when you do the math, okay? We can go through this if you want, come to my office. I'll show you how you actually calculate this, okay? ASTM, that's what that bag says, okay? If you're not familiar with ASTM, okay, they shortened it, but this is basically American Society of Testing and Materials. This is just an organization that says, hey, if you want to put a stamp on your material that says it does this, whatever this is, you can make up a standard and says, I want to test it by, you know, I want to drive a 2-ton truck over it and then drop a bowling ball of 12 pounds on it, and if it passes certain performance standards, you can say it does that, whatever that is. Okay, that's a little bit confusing. All right.
How widely are ASTM standards?
And materials characterization very wide,
Okay.
very, very wide. And you'll also see, basically if you're trying to break into a market, and if there's an ASTM standard, you have to pretty much abide by it. Okay? People want to see that. Okay? And anything, you'd be amazed at what's out there, okay, with ASTM standards. Pretty much everything we'll see. If you look on the side of any kind of material, for the most part, it may say conforms to so-and-so ASTM standard, okay? So if you wanted to make a new material and say it's compostable, all right, you have to conform to ASTM standard 6400D, okay? And all of these are listed on the website, okay? There's also some other ones called ISO, same idea. If you see ISO and some number, that's the same concept, okay? So this is an example. I should have used this as opposed to the drop a bowling ball. This is carbon-14 dating, okay? There's 3 different ways you can do it. You can do it method A, method B, method C, vice versa, okay? Essentially, you oxidize the polymer to carbon dioxide, and then you measure the ratio, okay? There's 3 different ways you can oxidize and measure. Pick one, and you're fine, okay? But essentially, you'll have to know the answer and how much precision you need out of it, okay? And then you can say it meets these standards, or it doesn't meet these standards, okay? Just a way of saying if your material measures up, okay? We talked a little bit about this. So what does biodegradable really mean, okay? Because there's an ASTM standard to be defined as biodegradable, okay, it has specific meanings, okay? So when we're thinking about polymers being biodegradable, the whole process, essentially, you take this giant ball that we talked about, okay? And you wind up, the first step is actually chopping all these big chains into much smaller chains, okay? Just like humans can't handle that big, like if you wanted to eat polycarbonate, okay? You wouldn't be able to handle it, all right? The organisms, the microbes, can't handle it either, okay? So the first part is you have to break it down into much smaller bits, okay? You're not actually losing any mass in this first section. You're just chopping the chains in half, okay? And now that you have much smaller chains, the microbes can kind of get at it, okay? And convert this big ball of plastic into carbon dioxide and water, okay? All right, so the idea is basically turning any kind of carbon source for something to be biodegradable into only CO2 and water, okay? Here is actually what you see in a typical polymer degradation test. You have this lag phase, okay? And you've thrown this thing in some beaker and you sent it off to some lab and they're testing it, okay, under a set restricted standards, okay, a test. And so what they're doing here is, this is when all those chains of the giant molecule are being chopped up, okay? So it's like just taking scissors, okay? You're not actually getting rid of anything. You're just chopping the chains up, okay? So you don't actually see any weight loss or any conversion to CO2, okay? But once you get through and the chains are small enough, the microorganism will take over and you start to chew it up, okay? Until you get to a saturation level where there's nothing else that's accessible to the organisms, okay? And that's your percent biodegradation degree, okay? Everyone kind of get the idea?
When you say nothing's left that's accessible to the organism, you mean literally it's all gone?
The idea is ultimately to be left with CO2 and water. That leaves, okay? Whatever is left is the organism can't chew it up, essentially, or process it, okay?
But what the organism has eaten is actually now little tiny pieces of plastic.
Yeah, it's doing a chemical process. It's transforming all those little pieces of plastic into carbon dioxide and water.
But it can only do it with 65% of it?
This is just an example, okay, of what the typical degradation of a plastic would look
All
like.
plastics or just bio-based?
No. Example of what anything would be, okay? Yes?
So I guess the question is, what's going on with the remaining 35%? It's just sitting there as plastic.
just sits there, essentially. It's the leftovers. Okay.
Are there nanobot techniques for degrading it, or also chemical techniques? I mean, like just putting sulfuric acid on it?
Yeah, you can do that. That's how they digest cellulose, for the most part.
Or burning it at a really high temperature?
You can do that, yep. But I wouldn't call that biodegradation.
That's what happens to almost all of our plastic, because we can send it to a transfer station and the stuff that doesn't get recycled gets burned.
Yes, exactly. Exactly. So, yeah, you can do that, but that wouldn't classify as underneath this terminology of biodegradable. Okay? All right, so in this ASTM standard, there are 3 things that are important. Okay, students don't ever make slides like this with a bunch of words on them, okay? If you do, just highlight a couple of them. Essentially, is that microorganisms need to consume the carbon and transform that into, or consume the polymer here, and transform that into CO2 and water, okay? This needs to happen in a reasonable time frame and in a specified environment, okay? That's the last part that people don't really get, okay? Composting is one thing. That's such an environment, okay? If you throw it in a compost pile, it has a set of standards. It has to happen in 180 days, okay, in a compost pile. If you take that same piece of plastic, all right, and throw it in the ocean, all right, it has a different time frame to conform to, okay, and a different level. I think it's actually much more strict for a marine environment, okay, to do it. So you have to meet higher standards, essentially, okay? If you want to throw your waste into an anaerobic composter and say it's biodegradable, it has to meet this standard, okay?
So it has to meet the 7081 for you to chuck it in the ocean?
Yeah, essentially, for you to claim it's marine biodegradable, okay? I was on a call today with someone from Maine Bioplastics, and they're telling me about these lobster golf balls that they made. They're basically made out of the shells of lobsters. It's a polymer called chitosan. Okay, it's a pretty rigid polymer, and so essentially, if they wanted to say that those golf balls, when they hit them off the cruise ship into the ocean, pretty absurd idea, right? Are biodegradable and they're not doing anything that unenvironmentally friendly, they have to meet this standard. Okay, they have to take their golf balls and test for this standard. Okay, and then they could do that. So here is a whole list of everything. You'll see that if you want to throw it in a composting facility, depending on even what it is, if you want to test the inside of your, I can't remember the name of those Green Mountain coffee cups, essentially the international paper cups that are out there. Those all have PLA linings. Okay, it has a set standard for that. Because they wanted to standardize that, okay? This is the composting one. If you want to throw it in soil mulch, okay, you want to use this standard. If you want to throw it in the ocean, you use this standard. If you're going to just take it to an anaerobic digester and turn it into methane, you'll see this standard. I used to have some plastic bags that said biodegradable on it, and they were sold here at A and B. I think I bought them during my interview, and they said ASTMD. This makes no sense whatsoever because there's not an anaerobic digester anywhere around here. Okay, so it makes no sense to sell this in an area where there's no disposal infrastructure for it. It just goes in the trash pile. Okay, with everything else. You may feel good about buying it initially, but if you didn't check the label, you really didn't do anything better than buying the regular old hefty bags. Okay?
And so what does the label say? What's that number?
This one? This says D5511, ASTM D5511.
The significance of that number?
That tells you that this number, I don't know why it's this number, okay? It's whatever came up next in line, okay? I don't know why it's 5511. Okay, but this number means that it has to go. This is linked to this facility. Okay, so if your disposal infrastructure is an anaerobic digester, it has to meet this standard or this test to say it's biodegradable.
So they expect the consumer homework to memorize all of these and then check them.
They're giving you the information. It's your job to be informed about it. And to ask questions. If they claim that it's biodegradable, they should have a standard on it. If not, call them up and ask them. Okay? All right, so the oxo-biodegradable debate. Okay? This is actually pretty hotly debated. Okay? If you go to any polymer conference, where people are really geeking out on polymers, this comes up. If you go and sit in the bioplastics, this idea, are oxo-biodegradable plastics okay? Okay? I'm going to show my bias here about this, okay? In some ways. But their definition, okay, this is the Plastics Institute definition, are conventional plastics, polyethylene, polypropylene, polystyrene, fossil fuel-based polymers, okay? Where they've added something into it that will artificially chop up the chains, okay? The microbes aren't going to chop up the chains initially. They're going to add something into it. That something they add into it are typically metal salts, okay? Cobalt, lead, iron, okay? These will oxidize in air and ultimately oxidize the polymer and break it down into smaller bits, okay? Once it's in smaller bits, if those bits are small enough, the organism can then get a hold of it and use it as a food source, okay? Most of these do not meet ASTM D64 standards, okay? And most of that is because of the metal amounts that's in there, okay? There's actually a metal clause in there. It must be under this level of metals, okay? They tested some of these, okay? There's all kinds of problems. This is the first generation of it. I think this EcoSafe bag is actually the same company that makes the bio bags, okay? And they've changed completely the way they've done it, okay? I think they got really bad press after this report came out. It changed the way they did it. But they found moisture delays the onset of biodegradation, okay? High levels of metals, okay? And then they found that it varied from bag to bag, okay? You weren't getting a consistent measure, a consistent product, okay? And this is the certification, kind of the people that do the testing for you, okay? That will put your stamp on your package, okay? Here is the debate, okay? What's the difference between these two life cycles? The one on the left is the Oxo-Biodegradable Plastics Institute, and this is the renewable cycle we saw before. What's the difference? Anyone? Yeah, 1 million years, give or take. Okay. So this is a big circle on the left. Okay. But here's where I have a problem with oxo-biodegradable plastics, okay, versus any other piece of plastic. What happens is those bags, say you have a trash bag, okay, that's oxo-biodegradable, all right? After a short amount of time, that will fragment into a bunch of little pieces, okay? If you've ever been to a disposal place, essentially a dump that uses oxo-biodegradable bags, it's littered with fragments of all these little bitty pieces of plastic all over the place, okay? And they're picked up by the wind, they get blown into the ocean, they get blown into anything that's around, okay? And what those are tiny sponges because they're all still polyethylene and polypropylene. They're still very hydrophobic, okay? And you dump that into a landfill, that's a sponge for all the toxic chemicals that are there, okay? So what you wind up having is you have this small piece of plastic that is soaked up huge amounts of toxic chemicals. Well, then all of a sudden birds come along or anything else comes along and eats that, all right? And then we wind up eating the birds or, you know, up the food chain it goes, okay? And as the animal gets bigger, it typically has more fat. These things are hydrophobic and will dissolve in the fat and deposit in there, okay? This is why tuna typically have a lot of problems, okay, because they're very fatty fish, okay? So a lot of things will dissolve in their fat, and then we wind up eating them, okay? So this is this idea of bioaccumulation. I saw a hand. Yes?
Yeah, might it be better to concentrate the toxic chemicals than to let them be
that's one, if you can contain them. Yeah, maybe. If they're going to be used, I'd rather have them in one place than all over the place. Yeah. So, interesting thing to think about. Okay, so let's get to something that makes everyone happy. Okay, everyone's scared. Compostable plastics. Okay, the main one that's on the market that you'll find nowadays is polylactic acid. Okay, and this is all our cups. Okay, that are out there, and most of our cutlery, I think, is either PLA based with starch added into it, or it's the same material that the bio bags are made out of that are hand drawn. That's called Matter B. Okay, that's fairly common. That was the first really compostable plastic to come on the market. PLA has come on very strong. It's not a new material. It's been around for over 100 years, I think, for the most part. But now it's really been commercialized, and people are doing it fairly economically. These are the beads. Okay, it's kind of a clear plastic. Problem with PLA is that it doesn't dissolve in anything. Okay, for the most part, and so it's fairly difficult to process. Okay, it doesn't like water. If you use a lot of water in the process, okay, it winds up chopping chains. Okay, so as you're forming your cup, all of a sudden your cup is actually the properties that you started out with are not going to wind up what you end with because you added moisture into it. Okay, so it is a fairly difficult material to work with. But under the right conditions, it will meet the ASTM standards, okay, for compostable. All right, so you need the combination of, and this is important, it has to be continuous, okay? Continuously above 60 degrees C, okay? This is why they typically don't break down in our backyard composter or a facility here, okay? We cannot get the temperature that high all the time. For 60 days, essentially, is what you need, okay? You need the right humidity. You need high humidity, 80% to do it. And then you need the right type of microorganism, okay? So all of these compostable plastics typically will say, and they're very upfront about this. It may not be on the sleeve of the material you buy, but if you go to their website, they say only compostable in an industrial composting facility that can maintain these conditions, okay? They're very upfront, and they even will give you a link that will tell you where these composting facilities are, okay? So if you're interested in that, go to NatureWorks. I think it's natureworks.com. You just do a quick Google search, NatureWorks, all right, PLA, and you'll get to their website, and you can find that composting facility list fairly quickly, okay? A lot of those composting facilities may not take PLA, though, okay? From what I know, I don't know if there's any in Maine that do, okay? So if we're going to continue to buy these cups, we need to probably deal with the issue on site. So there are some things that we can do, all right, if we think about it.
I have a quick question about the compostables.
Yes.
In the case where there isn't a facility,
yep,
do they last a shorter amount of time in the environment than comparable plastics?
Yes.
Plastics?
Yeah, they will. They will break down quicker. Now, whether that's, you know, if say it takes a plastic bag, like a polyethylene bag, 150 years to break down or something in your landfill, this may take 60. Okay, it just depends on the conditions in your landfill. Okay.
But it never breaks down all the way; it just breaks down till it's out of sight.
No, I mean it's kind of no. It'll break down over time, over a long period of time. Yes, I mean there are bacteria that eat oil. Okay, that's what people are claiming happened to our oil spill in the Gulf, right? So there are bacteria that will handle large chains, aliphatic chains, which most of these plastics are. Okay, you just have to get the two together to hang out together. Okay, and one will eat the other. Okay, there are organisms out there. Okay, this is actual standard if you're really interested in it. Essentially, you got to have 60% carbon conversion for homopolymer, so that means one, not a copolymer. Okay, one monomer. Okay. So polylactic acid has to have 60% conversion to CO2. Okay, it needs to happen in 180 days or less. Okay, 3 months. It has to disintegrate to the point where it can pass no more than, so the actual material that's left over. Okay, this goes to the idea of chopping up into really small bits. They basically just do a sieve test. Okay, and less than 10% of the total test material has to be left on top. Okay, so 90% of what's left has to go through that sieve. Okay, and then it has to pass the metals test. Okay, that we talked about, that the oxo-biodegradable plastics typically fail. Okay. So some suggestions. Okay, so in composting, we're actually chopping chains. Okay, we're breaking it down. That's what we want to do. All right. So ultimately, we want to break down this carbon-oxygen bond. Okay, here that would be a good first step. Okay. Who likes organic chemistry? Anyone? Okay, this is the mechanism on how we form esters. Okay. Yeah, I don't like it either. Okay. But if this is how you form esters, if you'll notice, there's a couple key points here. Okay. I've circled them for you. This is what you need to focus on. This would be your polylactic acid kind of hidden underneath this. Okay. So if you add water to polylactic acid, this is a reversible reaction. It's equilibrium reaction. If you add acid to it, okay, you'll drive it back to its starting material. So you'll break it down. Okay. It's a reversible reaction. Okay. So things that can help compost this material. Now I don't know if it's good for the microbes, but it would be good to break this material down. Are adjusting the pH. Okay. If you make it slightly more acidic, okay, I was thinking you could probably throw in your coffee, like a concentrated coffee grounds or pine needles. That would lower the acidity, the overall acidity in your compost bin. Okay, so you may get some help there. If you keep it at high humidity, all right, and increase the temperature. So I'm thinking that if you're a botanist, don't throw anything at me. The greenhouse may be a good test spot to do this. Okay, it's fairly humid in there. It's fairly hot. Okay, and what I'm ultimately thinking is if we really want to do a little pilot plant to see if we can get these things to break down, we're going to run it in a small batch. So then what we would do is throw our cups in with pine needles, coffee grounds, and probably some greens to balance the nutrients. Okay, wait for those cups to start to break down into the smaller chains. Then once they've initially broken down, we transfer them into the main compost bin. Okay, and when we restart a new batch with coffee grounds and pine needles. Okay.
Coffee will have enough nitrogen in it.
Will?
Yeah. And you have free coffee grounds downtown.
Cool. There's free coffee grounds in my office. So.
Volume that probably.
I don't know. We got a big bin already, so. All right. So these are at least some initial thoughts. I'd love to hear more about what's going on. Lisa's going to get me all the information on what is actually going on now in the compost facility, at least the temperatures.
Facility? I don't want to call it facility.
Okay. All right. So these are my thoughts on what could really happen. Okay. Whether it'll work, I don't know. Okay. I'm just looking at the chemistry of it and saying that it's doable.
Why, in the context of doing it at COA and trying to get the stuff to break down, why not just use acid? Why try and combine acid with the composting process?
Well, you have to neutralize that acid most of the time if you're going to throw it back in your compost bin. I mean, if we just want to throw it in the trash, we should just throw it in the trash. That's the thing. I don't really think it'll break down ultimately elsewhere. All right, so adding acid, we're now adding another problem to our disposal infrastructure.
How strong does the acid have to be? I mean, could it be acetic acid? Could it be orange juice? Or does it have to be really strong? Or?
Well, I mean, you have to do it needs to be somewhere in the range of probably less than pH 3 or 4. Okay?
It's probably not orange juice, or your cup would be melted when you're drinking your orange juice.
Yeah. Well, if you heated it up really high. I've actually noticed that those cups, if you leave water in them on a hot day, you'll come back and it'll be completely softened and your cup will be deformed. Yeah. Right, that's another you're not actually degrading the material. Kind of think of it as softening the material. But that's a first start. You're getting close if you're getting to that point. Okay. That's why I think these will help. These won't be the ultimate answer. Okay. It's going to be very much trial and error to do it. Okay. Yes, a lot of hands.
So in regard to the health concerns of endocrine disruption and carcinogens and stuff like that, is the compostable PLA, is that a mostly benign material? So that's
Yep.
not,
Yep.
that's not really major.
Here's a good way to look at kind of the breakdown of what PLA is made up of. If you look at this is oxygen, carbon, oxygen bond. That's CO2. Okay. What's left over is really just ethanol. Okay.
So that doesn't have the same sponge effect of gathering hydrophobic.
A little bit. It will have some, not as much. Not as much. You do have all these oxygens hanging off here, and so water will want to hang around this. Okay, it'll hydrogen bond to that for the most part. See, now you're getting into polymer properties. Depending on its molecular weight and how the coil is, things like that, will depict its properties. Okay. Yes. Yeah.
This sounds really cool and exciting, but I'm still wondering about, this is in very specific conditions and you have to do a lot for it. So what about all the stuff that does end up elsewhere in the environment in all the right conditions? In the ocean, 80% of marine debris is plastic.
Mm-hmm.
And even though it's compostable, it still has those same properties that make it so detrimental to marine life. It's lightweight and it's super durable, and
Mm-hmm.
so it still doesn't feel like a whole solution. It feels like something that could be dangerous because it lulls us into feeling better about it.
I think the idea is that it's around for such a low amount of time.
Even in the ocean?
Well, it depends. You have to meet the standard, essentially. Yeah. There's a kind of exciting new material. If you extend this chain here, this one CH3, this methyl group, and make it longer, okay, that's a new type of material called polyhydroxyl alkanoates. Okay, those are made by bacterial fermentation. The bacteria actually makes the polymer. Okay. There's a company called Metabolics that makes those. That's currently used as, like, if you go to Target, their gift cards, I think, are made out of PHAs. I believe so. So those are fantastic materials. They're just really expensive. And they break down in the marine environment within the standards. I think they kind of set the gold standard for what it should be. Okay. And that will vary depending on this chain length, okay? But they're out there. We just have to get the cost down, essentially. Okay. So I'll just do a summary, okay? Polymers are basically, let's go back to this idea that polymers are kind of macromolecules as opposed to the small molecules that we typically think about. The nice thing, and I think that's kind of cool about polymers, is that they are tailorable to your needs. Okay, and this is why polymers are rapidly expanding in their usage. Okay, you just take a bunch of different monomers and combine them until you get to the properties that you want. Okay. Most polymers, I'm going to say most, there are some out there that are not, okay, they're non-toxic to humans, essentially, because you can't deal with it. It's such a big molecule. You can't break it down. But as soon as it does start to break down, it can be problematic. Okay, but the problems that we see typically that are out there now, people worried about things like bisphenol A, people worried about all the phthalates and the additives and the plasticizers. Those are the things we add into the plastic to make it useful. Okay, so you should probably yell at the manufacturers to change their plasticizers. Okay, not their plastic. In some ways, that's probably a more effective approach. Okay. The idea is really we need to design to the end of life and to our disposal infrastructure. Okay? If you are burning all your trash, that's a whole different scenario than if you are composting all your trash here. Okay? And so you'll have different uses. Okay? And different plastics will play a role in that. And then just be aware as a consumer. Okay? I'm sure a lot of people in here had no clue what those little standards mean. that you can go look it up, okay? And then this big thing is biodegradability is defined, okay, in 3 terms. By its percentage breakdown, okay, in the time it takes, and in what environment that it happens in, okay? So with that, thanks guys, and I'll take questions.